Hi, in this video we will see how to create a drainage network from the digital elevation model. Right now I have a file called Peninsular India 1K. It is a DEM with a resolution of 1000 meter. So 1 pixel represents area of 1000 meter by 1000 meter, also referred as 1K. So let's see how we can generate a drainage network from DEM. For that we need to use a command from a processing toolbox called as the r.watershed. So double click over here. Yeah, you have to give input file as a DEM. So here the DEM is Pen India 1K, that is a Peninsular India 1K. Then you have to provide the minimum size of the exterior watershed basin as a threshold value for the generation of the basin and the drainage network. For a time being I am giving this value as 500. So here I am deciding, or I am giving a watershed basin minimum value as a 500. So it is equivalent to 500 pixels. In my case the area of 1 pixel is 1 square kilometer, and therefore the minimum size of the exterior watershed basin here is 500 square kilometer. I can change this value, and depending on this value I can change the density of the drainage network. Higher is the value, lower is the density of the drainage network. Then I need to select algorithm for the DEM. So I am choosing single flow direction, that is a D8 model, and later on I have to give the names of the output files. So here the first output will be the number of cells that drain through each cell, so that is the flow accumulation. So I will create a folder called DMX1. So here I am giving flow accumulation 1K. So 1K I am just using extension for my convenience. Save. Then the second output is the drainage direction. Direction 1K. Then the another one is a unique label for watershed basin. You can give this as the then there is a stream segmentation. Save. Okay, I do not want these outputs, so I am turning those off at present moment. Then I will say run. So here it can take several minutes. It's all depending upon the geographical expanse and the resolution of DEM file. so you have to wait. It will show the over here that it is not responding, but in the background the operation is going on. Yep. So I will close this, and these are the outputs which are generated. Let's check them first. So this is the drainage direction. If I zoom it, I can see the values of each pixel using identifier tool. And so here the value is 8, here's the value is 1, 2, 2, 4. So here the values are ranging between 1 to 8. So these are the 8 direction in which water can flow, if you remember the theory of watershed delineation. So these are values are between 1 to 8. Okay, so this is the, so these pixels basically represents the direction of the flow within that pixel. Then let's go and see the flow accumulation. So this is how the flow accumulation layer looks like. So if you get such kind of representation, it means you need to go and make slight changes in appearance. So here I am choosing the cumulative count cut so that I can get rid of the extreme values. Yes, now I can get the better representation. So these are the flow accumulation, and you can see these values again using the identifier tool. So if I click anywhere, the value is 1, but if I click on this stream likes thing, then I can see some value. So here is 118, here the value is 384, so here the value is 997. So as you move downwards, downstream, number of cells which are contributing flow to that particular pixels increases. So here the count is 997. If I go further downward, here the count is 3629 cells. If I further go downwards, here is the say 6855. Okay, if I want to go further downwards, then I can further see the higher values. For example, if I see the value over here, so this value is around 0.2 million. So here the 0.2 million cells are contributing to the flow. And if I further move downward, so I am nearby a delta, then the value will be much higher, you can see. Okay, so these are the flow accumulation map. So it indicates the number of cells which are contributing flow to this network. Then let's see the stream segmentation. So these are the streams which are segmented over here. Now from this stream segmentation, this is again a pixelated or raster image. I want to create a drainage network which is a vector data type with the geometry as a line. So let's see how can we convert this raster data. So here if I check the value, here I will get the same value for each stream. So this is stream number 11142. So this is a stream number 11146. This is the stream number 11154. This is the stream number 11156. So these are the streams which were with multiple numbers, with different numbers. I can convert this into a vector by using a formula, or by using the command called as, first I will use the command called thin. So r dot thin, and I will select the input as stream segmentation, and I will store this thinned file str segment 1k thin. Save. I will say run. So it will also take several minutes. Okay, so it's complete. I will close this. Yeah, so let's see how thin looks like. So thin removes the additional pixels which are present in the raster file. So you can see there are some additional pixels over here, over here, over here, over here, over here, because at the end I want to convert this pixelated diagram into a vector geometry, which is a line geometry with the zero thickness by definition. So this strains thickness, the r dot thin module, this thinning operation removes the additional pixels. Okay, so once you do perform this thinning operation, later on you can convert this layer into a vector layer. Okay, we will see how to convert this layer into a vector layer. For that, um, we need to perform operation called r dot 2 dot vect. The input will be stream segmentation thin. The feature will be the line, because the vector will have the geometry of line, and then later on I can store this vectorized file as drainage network 1k. Okay, save, run. Again it will take some time. Yeah, so the operation is completed. Let's see what's the result is. Yeah, mm, yeah, so this is my drainage network. Now you can see this is a line feature, zero thickness, and these are the all lines representing the drainage network in the peninsular India. Before that, yeah, now you can see over here, so this is the these are the pixels which are from the uh, thin raster file, and based on these pixels the raster is converted into a vector. So now by this way you can generate a stream network from the DEM. So now you have got the stream network over here. Let's see whether we can do further analysis. Uh, while performing this operation, you see some weird values or weird shapes, weird colors in this region. This is not a landmass, this is a water body, and in case of digital elevation model, either there was no data, uh, and therefore algorithm couldn't calculate the values for this area when it was calculating the flow accumulation, drainage direction, all those things, and therefore you see all those errors over here. See, you can see all those errors in each of the map over here also. These errors are also known as the boundary effect, because on this boundary there was no data, and therefore these errors are there. Especially you see these errors in case of the area which is on western side of the Western Ghat. You can see over here, you can see all the drainage lines on the eastern side of the Western Ghat, but not over here. This is because DEM might be too big for this region, or this minimum size of the exterior basin which we have selected is too large, and therefore if you want to delineate the watershed over here, you need a DEM of higher resolution. Otherwise this will happen. So so you always remember, keep in mind about this effect. So therefore if you want to delineate a larger watershed, you should or any watershed, you should crop a DEM which is slightly bigger than the watershed. For example, if I want to analyze this area, I will slightly uh, crop a DEM with the additional buffer area, so I can get rid of this boundary effect. Now we will see how we can delineate a watershed with a given outlet. So I have this map of a drainage network, and you can see all these errors because of the boundary effects, and I have also loaded a Google satellite layer over here. Now let me just change the symbology. Okay, now I can see this thing. Now before delineating the watershed, I need to fix the outlet. Either I can fix the outlet over here without using the Google satellite. For example, if I want this point as the outlet, and then I will ask algorithm to perform the operation and identify the delineate the watershed. Or otherwise I can identify the outlet, for example, from the Google satellite map, and with the reference map I can identify the outlet. Or there is another way of doing the same thing is, if the outlet is defined. For example, if somebody asks me to uh, draw upper Godavari map, consider the Jayakwadi Dam as outlet, I will take the coordinates of the Jayakwadi Dam from the Google Earth, or from and I can export that file as a .kml file over here, and then I can trace those points over here, and I can select the appropriate point on this drainage network. So let's see how can we draw the uh, delineate the watershed. For that you need to use the tool, something which is called as the r dot water outlet. And if once you open it, then you need to first enter the raster map as the drainage direction. So drainage direction as the map, uh, and then I will put the coordinates of the outlet point. So I can put the copy paste the coordinates over here, or I can select the coordinates from the map. For example, let's, if I want this as the outlet as the coordinate, okay, so these coordinates are picked by the software, and then I can say basin 1. I will say save, and I will say run. So delineation has been done, and so this is the basin which has been generated. So this is the basin, you can see by selecting the outlet. So either I can select the outlet in this way, or I can also pick the outlet from the other sources, and I have to just enter the coordinate of that particular point. Now this basin is again a raster image, so in raster form, so I can convert it by using r.vect. So I will use that function r.to.vect, and I will convert this basin. This is the area, so I will keep this area as a feature, and I will convert this as the shape file. So this is a vector file with the polygon as geometry. Close. So if I take this all out, so this is the vector, you can see, and this is the drainage network. I will just put network above it. Yeah, so this is how it looks like. So in this case there are few things you need to remember. First of all, when you first of all you need to decide the what is the resolution of the DEM you are going to use. It will depend on the geographical expanse on which you are doing the computation. So for example, if I want to delineate this basin only, I will only crop and select only this much part of the DEM. I will not select the entire DEM, so that I can save on the unnecessary computation calculations by the algorithm. So appropriately I have to decide the resolution of a DEM. I have here selected 1K, which is a very large size of resolution, large size or resolution. I may go for depending on the size of the basin, I can go for 90 meter, which is provided by the SRTM, or I can go for 100 meter, 200 meter, 300 meter, 500 meter. This call has to take take this call. This has to be decided by the user or the operator. Second thing, the size of the exterior basin, minimum size. Again, I have selected this size as the 500 square kilometer, but again this can be uh, reduced. One can start with the 50 square kilometer, also the value can be 200, 300, 400, or 100, depending on that. You can increase the resolution, increase the density of the network. uh, yes, and in case of the water outlet, you can select the outlet from the map over here, or you can bring the outlet point from the other sources, for example Google Earth. You just need the lat long of the coordinates. Sometimes what will happen, if you are procuring the data from different sources, then at present I have selected this as the outlet, you might get the outlet which is just nearby, because there might be slight mismatch because of the depending upon the which coordinate reference system is being followed. So you may take the coordinate from the different source which will be near, which will appear over here, but while selecting I will select the coordinate from which is on the line, and I will ask system to delineate the watershed. So in this video we have seen how we can delineate the watershed, how we can produce a drainage network from the